Okay, welcome back. This is lecture 4. This is the second part of the lecture. And so the second part, I'm going to talk about limits and co-limits. These are sort of generalizations of the notions of products and kernels and co-kernels and co-products. And they're fantastically useful things. The definition is a little bit involved, but when you get used to it, it's not bad at all. A key component of the definition is the use of initial and terminal objects in categories. These were briefly defined in lecture 1, but they're sort of really central here. So I want to, in this sort of short segment, I'm going to remind you how initial and terminal objects work. If you're already completely happy with that, then you should skip this and go on to the next segment where I'll give the actual definition of limits. So here I'm just talking about initial and terminal objects. So the definition, so one is dual to the other, so let's, for the sake of making a choice, let us begin with terminal objects. So a definition. So D is a category, then an object, little d is terminal, if for every e object of d, there is a unique map exactly one map from E to D. Obviously, map means a morphism in the category D. Okay, well, I've written this carefully. So, yeah, a terminal object is an object which has a unique map from every other object. So, what is there to say about them? Let's just run through quickly some examples and exercises. So, an exercise would be show that a terminal object is unique up to unique isomorphism if it exists. So not every category has a terminal object, but a category has essentially at most one terminal object. Now, of course, if you have a terminal object and another object which is uniquely isomorphic to it, that will also be a terminal object. So we're not going to have one terminal object on the nose, but we're going to say, given any two terminal objects, there's a canonical isomorphism, indeed a unique isomorphism between them. So if D and D prime are terminal, show there is a unique isomorphism between D and D prime. This is a very easy exercise. Okay, so more interesting is to look at some examples. So what are the terminal objects if any, in each of the following categories? So I'll write a few examples on the board, and then maybe you want to pause the video and work out the answers, and then after that I will go through and tell you the answers, and you can see if you agree with me. So let's take sets, category 4 sets, or we can take, say, abelian groups, or we could just take groups. Or we could take the category of topological spaces together with, I guess I'm not saying what the maps are. Set is with maps of sets, abelian groups is with group homomorphisms as is group, and top is with continuous maps. And we could also take, say, I don't know, to make an artificial example, non-empty sets. This is not good notation, but never mind. The category of non-empty sets and the morphisms between them are what you think they are. Okay. So if you now want to pause the video and decide for yourselves what you think, firstly, whether they have a terminal object, and then what it is, and then restart the video, and then we'll go through the answers. So I'll actually stand here like a fool for a minute or so. Okay, welcome back. So I hope you've now worked out all of the answers. Let's go through them. So what's a terminal object in the category set? Well, does it have a terminal object? So the answer is yes. And so the terminal object in the category of sets is a singleton. So it's a set with a single object. So obviously there are lots of one-element sets, but indeed they're all uniquely isomorphic. They're all uniquely in bijection, so this is not so confusing. Every set has a unique map to here. Just send every element to that element. Notice that the other obvious candidate, the empty set, doesn't work. Almost no sets have maps to the empty set. So it's definitely not the empty set as a terminal object. Okay, So what about in the category of abelian groups? So then there's going to be a terminal object which is just the trivial group. How do we write this? It's a bit, I mean, yeah, a group with one element, and it's the
E.
Oh, E, yes, E is what I should call it. And for groups, it's rather similar. For all groups. Okay, for the category of topological spaces, again, you're getting the flavor of these things now. These are sort of small and boring examples. It's just got one element. And in the category of non-empty sets, so this example is here in order to facilitate the second half of the lecture. Right now, it counts as a trick question. Nothing interesting happened. Again, it's just a one-element set. Okay, you're starting to spot a pattern. We'll see later on when we start to do limits that there can be categories with much more interesting terminal objects, but this gives you some flavor of them. Okay, so let's do, that was terminal objects, let's do initial objects. So an initial object of a category is just a terminal object of the opposite category. Okay, for the sake of variety, I'll write down the definition in the same flavor. The definition, so D, objects of D is initial if it has a unique map to every object of B. If for every E in E, there is a unique map from, it says right around D to E. Okay. Equivalently, it's just an initial object is just a terminal object of the opposite category, the category with the arrows reversed. Again, the same exercise, now I replace this with initial, is true, and the same proof, the same argument essentially works. Okay, so now let's go through and let's bring back these examples. So this is my terminal object column. So in each of these examples, we can also ask what the initial objects are, if any. Okay, so once again, I'm going to sort of pause awkwardly for a moment. So the idea is that you will pause the video and you will work out what the answers are and then come back and we will go through them. Okay, welcome back. So I hope you had fun doing this. So what are the initial objects? So in the category of sets, we actually talked about this guy before. There is an initial object and it's the empty set. So the empty set has a unique map to every other set. It certainly has a map, so how do you specify a map of sets? You say where to send all the objects. Well, there are no objects to worry about, so that was very quick. Okay, so in the category of abelian groups, then there's, again, an initial object, and again, it's in fact the same as the terminal object. So the trivial group has a unique map to every other group, because group homomorphisms have to preserve the identity, there's nothing much else to be said. And it works the same way in the category of groups. On the other hand, the category of topological spaces, this is sort of more like set. Again, there is an initial object and it's just the empty topological space. So far things are a bit boring. What about, let's go down to our last example here. What happens in the category of non-empty sets? Now here things are a bit tricky. So we certainly can't take the empty set as our initial object because it's not actually in our category, so that's no good. It's very tempting to say, well, let's take the next smallest set. Let's take a one element set here. But that doesn't work. And the thing is that, indeed, a one element set admits a map to every other set, but it's not unique. So for example, from a one element set to a two element set, there are exactly two morphisms. So it's not enough just to have a map to every other set, you really need to have a unique map. So here it doesn't exist, so there is none. Okay. Now, so far we have not seen any examples where terminal objects don't exist, but here we can give a very cheap example. If you take the opposite category to the category of non-empty sets, then you see one. We will meet more interesting examples later on. Okay, that's the end of this bit. I can press my pause button.